Hello there, welcome to Scholar Tutors Online Tutorials YouTube channel. In this video, I'll talk about capacitors, what capacitors are made up of, factors affecting the capacitance of a capacitor, energy stored in a capacitor, and many more like that. Make sure you like the video and subscribe to our YouTube channel to get more valuable content in the future. Now let's get started. A capacitor can be defined as a device for storing electrical charges and electrical energy, and it is generally made up of two parts separated by an insulator, and this insulator can also be called the dielectric. Let's say we have a circuit running, and we have two parallel plates. We have the positive plate and the negative plate. Now there will be an insulator between these two plates. Now this is essentially what is called a capacitor, where you have two plates, a positive one and a negative one, an insulator in between them. This setup, as it is used for storing electrical charges and electrical energy. The charge Q it stores is directly proportional to the potential difference between these two plates. You see this positive plate, it has a potential difference on its own. This negative plate, it also has its own potential difference. The difference in the potential difference is what it's used to store charges, and this Q is directly proportional to the potential difference V. And from here we can say Q is equal to CV. You should note this formula, it is very important. Where Q is the charge itself and it is measured in coulomb, the V is the potential difference measured in volts, and C is the capacitance measured in farad. To know how well a capacitor store charges, we need to talk about the capacitance. The capacitance describes the ability of the capacitor to store charges. It is defined as the ability of the capacitor to store charges, and it is the ratio of the quantity of charge stored to the potential difference applied. It is this capacitance C is equal to Q over V. This is very important too. Capacitance is equal to charge over potential difference V. We've talked about a capacitor. We said it is used for storing electrical charges and electrical energy. Now let's talk about the types of this capacitor. The first one is the parallel plate capacitor. We have the cylindrical capacitor, spherical capacitor, concentric spheres capacitor. For the purpose of this tutorial, we'll only talk about the parallel plate capacitor. And the parallel plate capacitor is also like we described earlier. It has two plates and a dielectric or an insulator material in between the two plates. But how can we increase or decrease the ability of this capacitor to store charges? That leads us to the factor affecting the capacitance of a parallel plate capacitor. I summarize the factors affecting the capacitance of a parallel plate capacitor as DAND. D-A-N-D. D, the distance between the plates. A, area of the plates. N-D, nature of the dielectric or the insulator material in between the plates. Let's talk about each of these factors and how they affect the capacitance of a capacitor. For the distance, capacitance generally increases with decrease in the distance between the plates. That is, capacitance and distance are inversely related. If you are having an increase in capacitance means a decrease in the distance. That is, you have C is inversely proportional to D, and you have C is equal to K over D. From here we can say C1 D1 is equal to C2 D2. You can use this formula when you have maybe just C1 and you ask to find C2 without the other variables. So you can use this formula. But take note of this one. This one is very important. Let's call it equation 1. Now let's go to area of the plate. Capacitance increases with increase in the area or the size of the plate. That means they are directly related. It means as C increases, area also increases. We can say C is directly proportional to A, So C is equal to Ka, and C over A, C1 over A1 is equal to C2 over A2. You should take note of this relation. Let's call this one equation 2. We're trying to get to something here. Now let's go to nature of the dielectric. The dielectric material is an insulator placed in between the plates of the capacitor, like I said earlier. The stronger the dielectric strength of the dielectric material, the greater the capacitance. That is, capacitance and dielectric strength is directly related. So if you have an increase in capacitance, then you have an increase in dielectric strength. Let's call the dielectric strength, let's call it K. Please note it is different from the other K we've been using. So we can say the capacitance is directly proportional to K. So you can note this too. Let's call this one equation 3. Let's find a way to combine equation 1, 2 and 3. So we can say C is is inversely proportional to distance, directly proportional to area, and directly proportional to the dielectric strength. C is inversely proportional to distance between the plates, directly proportional to area of the plate, and directly proportional to dielectric strength. From here, we can say C is directly proportional to Ka over D. We can introduce a constant here. We can say C is equal to E naught Ka over D. This K is the dielectric strength. Let's assume the dielectric material, let's assume it's air or vacuum, or there's no dielectric material there. So K for air or vacuum is equal to 1. So we can say C is equal to E naught A over D, where E naught is the permittivity of free space. This is how we arrive at this popular formula for capacitance. We've talked about the capacitance of a capacitor. Now let's talk about how capacitors can be arranged in a circuit. How do we put them together to make a functional circuit? Capacitors can be arranged in majorly two ways. The first one is in series and the second one is in parallel. In series arrangement, capacitors are arranged that the positive plate of one capacitor is connected to the negative plate of another capacitor. You can just assume this is a circuit and you have a plate, this you have plates of capacitors. Now this is, if this is the positive plate and this is the negative plate, negative plate is connected with the positive of another one and it is connected with the negative, so we have like that positive. So we have positive plates connecting to negative plates, and let's say this is capacitor 1, capacitor 2 and capacitor 3 in the circuit. Something worthy of noting is that in series arrangements, the capacitors have different potential difference. They have different V. Different potential difference pass through them. However, they have the same quantity of charge, the same Q. To calculate the total potential difference going through this capacitor, we can say Vt, that is the total potential difference of this one, and this one. Vt is equal to, let's say this is V1, V2 and V3, is equal to V1 plus V2 plus V3. But remember, we said Q is equal to CV. That means V is equal to Q over C. We can also introduce that concept here. We can say Q, since the same quantity of charge flows through them, we have the same Q. So we can say Q over C, the C total, is equal to Q over C1 plus Q over C2 plus Q over C3. If we decide to factorize this, we can say Q open brackets 1 over C total is equal to Q open brackets 1 over C1 plus 1 over C2 plus 1 over C3 in big brackets. Q can cancel on both sides. So we have 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3. This formula is very important when calculating the total capacitance or the effective capacitance of a capacitor in series arrangement. You should never forget this formula. Let's talk about parallel arrangement of capacitor. Parallel arrangement is quite different because similar plates of the capacitor are connected together. Assume you have a capacitor, you have these capacitors. Now, these plates of the capacitor are connected together, similar plates, that is, let's say positive plates together, they are connected together. If this one is positive, this one too is positive, this one is positive, negative, negative, negative. The similar plates are connected together. And what happens in this case is that the charge flowing through the capacitors, it splits. The charge coming, if Q is coming, you have Q. The charge, when it gets here, it splits to three directions. The charge splits. I want you to take note of this, it is very important. The charge splits, but they have a common potential difference. The potential difference remains the same. I can decide to call the charge coming, I can decide to call it Q total. So as it splits, I can decide to call this one Q1, this one Q2, and this one Q3. So Q total is equal to the sum of the individual charges, the sum of Q1 plus Q2 plus Q3. But then remember, Q is equal to CV. So I can decide to represent all these things. I can decide to represent them as CV. So Q total, remember, in this scenario, V remains the same. So we can say C total V is equal to C1V plus C2V plus C3V. So we can say V open bracket C total is equal to V open bracket C1 plus C2 plus C3. Then we have CT, V we cancel on both sides. So we have CT is equal to C1 plus C2 plus C3. This is very important. This is the formula you use to calculate the total capacitance or the effective capacitance for a capacitor connected in parallel arrangements. I also want you to know that when capacitors are arranged in series, the total capacitance or the effective capacitance is always smaller than the smallest capacitance. You see, in that formula, it is adding 1 over this plus 1 over this. So when you finally add all the 1 overs together, it is smaller than the smallest capacitance in that circuit. But then in parallel, it is different. The total capacitance is always larger than the largest capacitance in the arrangement. So you should note this. They are just opposite each other and it is very simple to learn. Let's talk about the energy stored in a capacitor. In the process of charging a capacitor, the capacitor actually does work, and this work that it does is known as the energy stored in that capacitor. It is defined as the work done in charging the capacitor. If the quantity of charge is plotted against the potential difference between the plate of the capacitor, if it is plotted on a graph, the graph gotten will be a straight line graph and the slope will give the capacitance. Assume we have something like this. We have a graph Q, which is the charge plotted against the potential difference V to give you a straight line graph, and the slope of this graph, this slope S, the slope will give you Q over V. And if you remember, we said Q is equal to CV. So Q over V is equal to C. So you can say here that the Q over V is equal to C, which is the capacitance. In this same graph, the area under this graph is known as the work done, is the actual work done. This is a triangle. So you can say work done is equal to area of triangle, and this area, we say this is Q and we say this is V. Area of triangle is half base times height. The base in this case is the V, while the height in this case is the Q. So we can say the area is equal to half QV, which is also the work done. W is equal to half QV. You should note this, it is very important. W is equal to half QV. But then we can still generate a lot of things from this formula. Since we said Q is equal to CV, abi, so we can also bring this Q, we can bring it here. So we can say W is equal to 1 over 2 multiplied by, since Q is CV, we can say CV multiplied by V. We get W is equal to half CV squared. You should note this formula, it is important. So W is equal to half CV squared. These are formulas to calculate work done by a capacitor or energy stored in a capacitor. From here we can still go further. We say W equal to half CV square, abi. You can, if we can, from here we can say V is equal to Q over C. So we can put that value here. So we say W is equal to half C, and this time around we use Q over C. So Q over C squared. So we have W is equal to 1 over 2 multiplied by C multiplied by Q squared over C squared. C will cancel one of the C. So we have W is equal to half Q squared over 2C. We have W is equal to half 1 over, or we can just say Q squared over 2C. W equal to Q squared over 2C. This is very important. You see, these three formulas are very important to solving energy stored in a capacitor. You should not forget this formula. So whenever you see a question that asks you for energy, you can just come back to this formula. Use this formula to solve it. Write down your parameters. After you write down your parameters, put in your parameters in the formula. Look at this formula, look at the one that works for it, look at the parameters you are given and compare it to the formula. Input your parameter in the formula and solve your question. We finally come to the end of this video. We talked about what capacitors are made up of, factors affecting the capacitance of a capacitor, arrangement of capacitors, and many more. If you enjoyed this video, please make sure you like the video and hit the subscribe button so you can get access to more valuable content in the future. Thank you for watching. I'll see you in the next video.